In this video, we're going to use the chi-squared distribution, a chi-squared statistic, to do a goodness of fit test. So the scenario we're going to look at here is Chifaru found a chart that her mother made of her candy that she got in Halloween in 1985. Right? And then she made a chart of her Halloween candy in 2015. So Chifaru's mother got 15% Snickers, 18% Kit Kats, 27% Smarties, 24% Reese's, and 16% of other. Whereas in 2015, Chifaru got 68 Snickers, 67 Kit Kats, 87 Smarties, 79 Reese's, and 59 other pieces. So 360 pieces of candy overall. So she wants to see if the proportion of candy really changed over 30 years. I mean, the odds are she's not going to get the exact same amount, exact same proportions that her mother did. But is this difference enough to say that the distribution of candy has really changed over that time? We're going to do this with a standard hypothesis test. This is something that we've now talked about quite a bit. All right, so we're going to slightly modify our hypothesis test. The main pieces are the same. We're going to have a null and alternative hypotheses. In this case, the null hypothesis is going to have several pieces to it. It's going to be that each of the proportions, Snickers, Kit Kats, Smarties, Reese's, and other, are going to be the same. Right? The new proportions are going to be the same as the old proportions. The alternative is that at least some of the proportions are different. We can't really do left or right-tailed tests because these are proportions. If one of them goes up, another one has to go down to compensate. So we really can't say greater or less. So we just have to say that some of them have changed. The rest of it is going to be similar. We're going to have a level of significance. We're going to have some test statistic. Previously, we had T for a student's T distribution, or Z if we were able to use the standard normal distribution. This difference is going to be a little different, so we're going to use a chi-squared. We're going to have a chi-squared distribution that we'll talk about in class. We're going to use that test statistic to calculate a p-value, and then it's this p-value that we will compare with alpha to determine whether or not to reject or fail to reject our H naught, and those are going to be the same. If the p-value is smaller than alpha, we're going to reject the null hypothesis and accept the alternative hypothesis. If the p-value is larger than alpha, we will fail to reject. There's not going to be enough evidence to overturn our null hypothesis, and then we're going to have to make some conclusion based on what we found. So the null hypothesis is going to be that the proportion of Halloween candy is the same in 2015 as it was in 1985. So statisticians don't like to work in percents, we like to work in proportions. So our null hypothesis is going to be based on the proportion. Snickers was 15%, so that's 0.15, Kit Kats 0.18, Smarties 0.27, Reese's 0.26, and other is 0.16. Now, since Chifaru had 360 candy pieces in 2015, if the proportions were exactly the same, we could do a calculation to figure out what we would expect the number of each type of candy to be, and we're going to get what's called our expected values. So to calculate our expected values, it's the number times the proportion. So it's going to be, for Snickers, 360 times its proportion of 0.15. So we would expect 54 out of the 360 pieces of candy would be Snickers. For Kit Kats, its expected value is going to be the total number times its proportion, 360 times 0.18. We would expect 64.8 pieces of candy, right? We can't have a part of a piece of candy, so we will never be able to get this one exactly. Smarties, its expected value is 360 pieces times its proportion of 0.27, so we would expect 97.2 pieces. For Kit Kats, 360 times its proportion of 0.24. So we would expect 86.4 Reese's. For our other, its expected value is our 360 pieces of candy times its proportion of 0.16. So we would expect 57.6 pieces of just miscellaneous. In terms of vocabulary, these are our expected frequencies, and they're given the letter E because of expected. E1, E2, E3, E4, they are related to their specific p-values. Right? And we simply number them in a nice systematic way. So if we put our expected values, our 2015 expected values on our table, as well as our what we call observed values, this is the numbers of pieces of candy we actually got, right? So Snickers would be 01. We observed 68 pieces. We expected 54. 02. We got 67 pieces of Kit Kats. We expected 68.4. 03. Smarties, we obtained 87 pieces. We expected 97.2. 04. We observed 79 pieces of Reese's Pieces, and expected 86.4. We observed 59 of other and expected 57.6. Right, so these are the numbers that are going to be the same. The test statistic, right, our chi-squared, this is going to measure how well the expected data matches the observed data, right? The observed data is the thing we get from reality, and the expected is what we get from simply projecting our past model forward. The closer each of the observed and expected values for each category is, the smaller chi-squared will be, right? If they perfectly match, chi-squared will be 0. And the more different they are, the larger chi-squared is going to be. And we'll talk about exactly how to calculate this in class. So this test statistic, chi-squared, is used to calculate a p-value from a chi-squared distribution, right? We will have some distribution, we're going to have some test statistic value, and the p-value is going to be the area under the curve going outwards from that point. And again, I will talk about this in class. There's one more piece of information that we use for our chi-squared distribution, and that's our degrees of freedom. In this case, the degrees of freedom we're going to use is going to be one less than the number of categories. Right? So we had 5 different types of candy, so we have 5 categories. So we had 5 categories, 5 minus 1 is 4, so we're going to have 4 degrees of freedom in this case. Previously, degrees of freedom was 1 less than the number of data points, but in this case, our categories are taking that place. So our degrees of freedom is going to be 1 less than the number of categories that we're using. So these are standard calculations, right? So we have the ability to do these on a TI-84. But first, let's define our terms, right? For a null hypothesis, for a hypothesis test, is that our proportions for our 5 categories are the exact same in 2015 as they were back in 1985. Our alternative hypothesis is that there's going to be some difference in the proportions claimed. We're going to have to choose a level of significance for this. Let's choose 0.05. It's a pretty reasonable one. If we could go lower if we want. We could go higher if we wanted, but let's choose 0.05 in this case. Now to do the test on a TI-84, what we want to do is we want to enter our observed values. That's the pieces that we actually got in 2015. We're going to enter those into list 1. Our expected values we're going to enter into list 2. Then to do the calculation, we hit the stat button go over to tests, and we look for the chi-squared goodness of fit test. You usually have to go down quite a bit. Since we put the observed values in list 1, the observed we say is going to be list 1, our expected is going to be list 2. If you put the lists in different places, you would just say whichever list it was the observed values is the observed list, and whatever value is the expected values, that's going to go in the other list. We have to tell it the degrees of freedom. In this case, we had 5 categories, so we're going to have 4 degrees of freedom, and then we hit calculate. You could also look for the plot, and that actually shows you the chi-squared distribution for 4 degrees of freedom, as well as the shaded area for our p-value. But in this case, let's hit calculate and look at the output. Right, so the pieces of our output, the first thing is going to be our chi-squared. That's going to be our test statistic. That's going to be the place that we're looking on our graph. The p-value is the amount of area under the curve of our chi-squared distribution, right? And this is the thing that we're going to use to compare, right? This is the probability that, assuming the null hypothesis is true, that we get values as extreme as the ones we had. The degrees of freedom, well, we just inputted this, 1 less than the number of categories, in this case 5 categories, so 4 degrees of freedom. The last piece of the output, CNTRB, it's going to give 5 decimal values, 1 for each category. And it tells you how much of the contribution of the chi-squared is for each category, right? So there's going to be 1 value for the Snickers, 1 value for the Kit Kats, 1 value for the Smarties, etc. If you add those 5 up, those 5 are going to be equal to our chi-squared. So this is how much each category difference contributes to that chi-squared. But for the hypothesis test, since we have access to our p-value, let's use that to do our evaluation. So our alpha value was 0.05, our p-value 0.2448 is certainly larger, it's higher than our significance level. So what does that mean? We are going to fail to reject the null hypothesis, and there's not going to be enough data to support switching over to the alternative hypothesis. So we use that to construct our conclusion. And our conclusion is, there is not enough evidence to say that the proportion of Halloween candy is different in 2015 than it was in 1985. So look over the section, and we will see you in class.